Welcome to this session where I show you how the class data sharing option of the JVM can speed up your Java application startup. When you access a Java class from your program, various steps are performed before you can use that bytecode, that code which is written in that class. First of all, there is of course the class loading itself. There are various class loaders. And when the class is found, then the verification, preparation, and resolving is performed first to make sure that everything is okay with that class, that it can safely be used. The next step is the initialization, like static variables which are initialized, and then afterwards the class can be finally used. So various steps are performed, which take some time, which are required because we need to have the certainty that a class is valid, that the loaded bytecode is valid. But of course, this slows down your application startup. And in this session, I'll show you how you can use the class data sharing of the JVM to improve that startup time without the need to rewrite any part of your application. I'm Rudy de Busscher. I'm working for Payara Services, and I'm there the developer advocate and technical salesperson. So I'm helping people getting on board on the Payara platform. So what are we going to cover today? First of all, a few JVM internals related to that class. Nothing too technical and not too deep, but a few options, a few aspects that you need to be aware of to understand what class data sharing is doing. Then a few words about why the fast startup is important. And then, of course, demos to show the feature in action and that you can see what benefits it can give you. So when you specify the statement new my class in the code, then various actions are performed. First of all, the bytecode is loaded from the external system, most of the time your disk, through one of the class loaders. Then that bytecode is verified. We need to make sure that the JVM is capable of running that bytecode because in newer versions there are newer bytecodes created, for instance, for the record construct, and that means that there is a verification required to see if it is valid or not for that version. But also a verification to see if there is no tampering done with that bytecode, with that class. Because the compiler creates that bytecode, but you can manually change that bytecode, and then you can have the basis for a malicious attack on your code. So you can have a look at the internet. There are various resources described how you can manipulate the bytecode so that you can bypass some of the things which the JVM normally does. And the Java compiler is not the only one who is creating bytecode. You have also those JVM languages like Kotlin or Scala, which create bytecode. So it is a very important step, this verification, and should not be disabled. Then a second step is the class file derivation, which can result in that incompatible class change error, which some of you already encountered. In this step, the statements are verified. For instance, if you call a method in another class with a certain parameter set, then there is a check if that method is still there, because it can be that it was there during compilation, but at the runtime you can supply another version. So the method signature is checked to see if it still is valid, if it still can be used, and that can result then in that incompatible class change error if that's not the case. The next step is the preparation. You can see it as more or less the variable initialization. There is also a resolution step for resolving symbolic reference, most of the time related with dynamic invokes constructs that you have, or that some libraries that you use in your application. And then the Java interpreter can use that code. So all these steps are required when you do that new my class, and some of them don't need to be done at runtime. For instance, that verification and that class file derivation, we could move that to a pre-startup step, and then that means that everything can go faster when you actually need the class itself. So one step back, maybe there are improvements. So what are the different options to improve? Because there is more than one option possible for a certain problem. As I mentioned, you can disable that verification, but that is a very bad option if you ask me, because that opens the door for malicious bytecode. So that's something that you should never do. The other alternative, which is very popular these days or gains attraction, is the native compilation of the Java code. But it has various downsides. It will improve in the future, no doubt about it, but for the moment it is slow. That means that it takes a lot of time before you have compiled your bytecode to native code. There is also a lower peak performance, so when your application is running, then the native code is fixed, so it cannot be optimized anymore. And because Java has such a long tradition of those optimization, the JIT compiler optimizations, that at the end, after a few requests, that the Java code is performing better than the native code which is generated. You also have issues with reflection. You have problems with debug code, with Java agents, etc. All those things are looked into and will have a solution in the future. But for the moment, native compilation is not a real solution for the problem of the slow startup, if you ask me. And then we have that class data sharing. The name is a bit confusing, if you ask me, because it's not about sharing data like static variables in classes, but it is that your class information can be shared between different JVMs. The option performs that verification and that method signature validation, and creates a specific format, a native format for the JVM, and puts all that information in a read-only memory mapped file, which can then be used at runtime directly and bypassing some of those steps which are done normally. And then you have a major improvement of your application startup, or in general, a major improvement when you use your classes. Then maybe the question why the fast startup is important, because it's not always obvious, or it's not always important in all scenarios. And I'm not talking about the cold startup problem here, which you have with serverless, but for a regular application, you still might have the need to have a application, a additional instance that starts up as fast as possible. Imagine that you have a system for ticket reservation. These days it's not a good example, but anyway, those systems still exist. And then, of course, if you announce a new event, then you probably will have a surge in requests because a lot of people want to buy a ticket for that event. And when your system is optimized to handle a certain amount of requests without any issues, up to that blue line that everything goes okay, then when the number of requests go over that blue line, then of course you need to start up a additional microservice, for instance, to handle your load the number of requests done by the users of your application. But starting up an additional instance can take a few seconds. And during those few seconds, you can have the fact that some connections are refused because there was all the queues were filled up and there was no room anymore to handle it. The performance will go down. Maybe there are a few people dropping out because they need to wait too long when they click on parts of your application, etc. So it is important to do the startup there as fast as possible. And maybe you can decide to start up an instance a bit earlier so that you're sure that you're capable of handling that load. For instance, there you see that little bump just before the large peak, but that did not go over that blue line. So if you decide to start up the additional instance, you might you end up with more instances than you really need, so more cost and more resources that are allocated. So the class data sharing, CDS in short, that does the load, verify, and derive steps that we discussed earlier. We perform that up front end so that you can use that the JVM can use that information from a memory mapped file immediately, and then the data is accessible much faster, and the class loading is faster. The memory requirements can also be lower because you can have that archive file shared between several processes, between several JVM processes, which means that your memory requirement itself can be lower, which can be a good thing if you run multiple processes in a cloud environment, for instance. And a simple hello world example, so the static main method where you just print out hello world. If you look at how many classes it uses, then you have 437 classes. Speeding up those classes, speeding up the loading of those classes probably won't make much difference. But for instance, Payara Micro, which is an entire runtime for your Jakarta web profile, if you start up there an application, then you use around 15,000 classes. So speeding up the class loading there will result in a very noticeable difference. For using the CDS, there are two differences. If you are using an OpenJDK based JVM like Azul, then you have the option to specify the loaded class list because the system needs to know which classes need to be prepared. So that's the option that you then need to use. You also have an option to indicate the archive file that he needs to create or use, and the XX share dump or on parameter defines if you want to create such an archive file or just use that file. For OpenJ9, you have only one option, which is called -x share classes, where you have various options then to define all the same information, the archive file name, etc. And there the classes list are more created automatically, and it's discovered automatically, so you do not need to create that list up front and then supply it to the next step. So let's have a look how we can perform these steps, how the requirements are to use that CDS and what the end result is. So I have here an environment where I have a JDK 11 installed. It's the Zulu 11 version, as you can see. And the first thing that I want to do is to give you an idea how much time it takes to start a Payara Micro with a demo application without any addition, just without CDS, the normal way of starting up the application with Java -jar. the executable jar file for Payara Micro, and then a link to the location where the applications are available that needs to be deployed. So the Payara Micro instance starts up, and at the end it gives us an indication how much time it took to start up. And here now it says it has used 10 seconds to start up fully. So let us see now how we can improve that time when we use that CDS option of the JVM. So first of all, we need to create a specific launcher for Payara Micro because this executable jar file is first expanded, and then all the jar files and the classes in there are added to the class path. But the CDS option is very sensitive for changes in class path, which is very normal because changes in the class path could mean that another class could be picked up. So in order to use CDS, you need a very strict, stable class path. So this is then the first step that we need to do. That is that we expand that jar file, and we create a new jar file which is again an executable jar file, but this time we have a fixed class path that is indicated in the jar file which jar files and class files it will find, for instance, in this lib folder, so that we have a fixed and stable class path. Then the next step is to create that class list. The option requires, in the JDK 11 version, the option requires here to have the information of all the classes that it needs to prepare. Luckily, we can do that automatically, so that whenever the JVM now loads a class with that XX dump loaded class list option here, then it will record it in this file classes list. And to facilitate the creation and the usage with Payara Micro, we have created that -warmup option here, so which means that when the system is started entirely, then it stops again. So because we are only interested in that warm-up phase, so we don't need to have that instance running for handling requests. Now we have that classes list created because the JVM has loaded all the classes of Payara Micro. Payara Micro has inspected all the classes of your application, so that means all classes are loaded. And we have here a long list then, around those 15,000 classes. Some of them are from the JDK, other are from Payara, the old parts of Glassfish, but also some new files, new classes from Payara itself, for instance here for MicroProfile. And if you scroll more up, you would also find your own classes from your application. Now, in the next step that we need to do is then, based on that classes list that we have gathered, then we create that archive file, that memory mapped read-only file, which has that, which contains the optimized and prepared class information already. And we specify here again that jar file because the system needs to know where it can find the classes that we have specified here in the classes list. So we need to define the class path, of course. This is not a normal startup, of course, of your application. It's just creating that archive file. You see also that he says that he cannot find some classes. That's because of the fact that our dynamically generated proxy classes, which are only available at runtime, so not in the class path, and then you get that warning that it is not found, of course. Also, you see here a restriction of the CDS option. That is that older classes, namely classes compiled for 1.6 and older, cannot be used by that CDS option. So that is now a good excuse that you need to upgrade your dependencies to the latest version so that every class can be used in this CDS option. At the end, the whole process results then in a file which is generated. As you see here, we get the output of the different parts of that file, but we also see that the file is a rather big file. It is 161 megabytes in size. And as mentioned, that's a specific format, but it's also read-only, read-only for all users, so that we cannot change the file, because that file needs now to be trusted, because that will be added immediately to the JVM, and information is used there without performing any checks anymore. So that needs to be made sure that we are not changing that information or in some way, because then we can have an open door for malicious code executions. The size is rather big because it contains most parts of the JVM, it contains most parts of Payara Micro, and it contains your application. So basically, it contains your entire application. So you have more or less created a version of your application, a self-contained version where everything is located in one jar file, in one archive file, which is used then later on by the JVM to run your application. And then once we have that file, we can, of course, start using it. So we can again start up Payara Micro with this output launcher that we have created. We now say that we are going to use our archive file, and we specify that archive file. When we start up the server this time, at the end, you will see that it reports again the time that it took for starting up, and you see that it is only 7.3 seconds, so which is a lot less than that 10 seconds we had at the beginning. I can also quickly show you how we can do that with the OpenJ9 version of the JDK. So that's it's not OpenJDK based, so it is a little bit different. So I have here again the OpenJ9 version, the same based on the same JDK 11. And here the options are a bit different, and also the steps are a bit different. As mentioned, you have that share classes where you specify the name of the archive file and the location. So I'm using the current location. And I need to specify because the file, the archive file would be is rather large, and so I need more than the default size. I specify a maximum size of 300 megabytes. With the OpenJ9, I do not need to give the system a list of all the classes file that it needs to create, but it can create that archive file based on that warm-up phase that is available within Payara Micro. So I'm running the launcher with the warm-up phase with the correct information for the archive file, and then I get a startup, which is terminated when everything is ready because we have that warm-up property, and at the same time OpenJ9 stores all the information of the loaded classes in that archive file that we have specified. Then later on, using that archive file, then we only need to specify that xshare classes option again, and the launcher that we have for Payara Micro, and it starts up the server, the Payara Micro instance, using that archive file, and you see here that you have again around that 7-second startup time, so you have more or less the same benefits with OpenJ9 as with the OpenJDK based versions. So you have always various steps that you have to perform. You have more steps with OpenJDK as with OpenJ9. You can automate them, of course, when you are using a script, But when you have a Docker system, and when you use Docker for running your application, then of course you can perform all the steps as part of the build process of your Docker image. You need to take care, of course, that you have an optimal layering system. So the optimal solution is that you have a multi-stage build. The first thing here is that I start from that Alpine version of JDK 11. I copy Payara Micro there. I'm creating that launcher here. Then in a second step of the Docker file, I'm executing the warm-up step, where I create that classes list here for OpenJDK, and immediately followed by the actual creation of that archive file that we have. And then in the last step, we can just start up our Payara Micro instance using that archive file and indicating that the archive file needs to be used with the additional information of the memory usage for the Docker container. And this way we have a optimal Docker file which contains all the steps required to create that archive file and use it at runtime. So to get you the overview of the testing that we have done in a more controlled environment, then you can see that both the OpenJDK and the OpenJ9 version, you have a significant reduction in startup time. That the startup time is around 35% faster. There is a bit of memory change that you can detect, the amount of memory that is used, mainly because you're not doing that derivation process, that verification, which also takes, of course, some classes and memory to perform that task. So we spoke about the Docker images, so you can use also that shared archive file outside your Docker image on a volume, for instance. But you need then, if you're using plain Docker, and an extra step in your build process, or you can use the Podman build step, because there you can specify a volume during the build, which is not possible with the standard Docker command line. You need to be aware of a few pitfalls, which I already mentioned, the classpath issues, because it needs to be very strict. It needs to be identical when you're using CDS, then at the time when you have created that archive file. Dynamic proxies and 1.6 classes cannot be used. You have the option, if you encounter some issues, to specify the parameter -xlog to give you detailed information of what he is doing and what is going wrong. And it should be no surprise that that shared archive file is version, JDK version, and operating system dependent. So whenever you change your version, your operating system or your application, of course, don't forget to recreate that archive file. Thank you for watching, and hope to see you in the Q&A immediately after this recording.